Welcome to Basic Electrical Engineering, Lecture 5. Today we will study nodal analysis. Nodal analysis is based on the famous Kirchhoff's current law. We studied KCL in Lecture 4. It says that sum of entering currents is equal to sum of leaving currents from a node. A node is a point where branches meet and current divides. This means that if we'll assume all the currents to be leaving most of the times, so if all the currents are leaving, this equation can be rewritten as, and there is no entering current, the KCL equation can be written as sum of entering currents, sum of leaving currents is equal to 0 if there is no entering current, which we assume for nodal analysis. What are the steps? First of all, we'll identify the ground node. Ground node is the reference node with respect to which all voltages are measured. Then for all non-ground nodes, we assume a voltage for all nodes that are non-ground. And then write KCL equation for each node. And we'll assume that the node for which we are writing equation has the highest voltage. Let's solve an example to be more clear. A 12K resistor, a 6K resistor, a 6K resistor, and another current source of having 4. This circuit contains two current sources of 4 milliampere and 2 milliampere each, and these three resistors. We need to find out the two voltages. First we need to find out to identify nodes. What's the first node? The first node should be the ground node, the reference node. The voltage of this reference node is 0 volts. It's the ground node or reference node. There are two other nodes in this circuit for which we can assume voltages. These are the nodes V1 and V2. Let's write equations, KCL equations for each of these two nodes one by one. What is the equation for node 1? Since we have this 4 milliampere current source which is directing current to be flowing into the node V1, so we are bound to take it as a negative. It's an entering current because we have already studied that all entering currents are taken as negative. So this 4 milliampere current is for sure entering into the node 1, therefore we write it as minus 4 milli because we are definite about it, it's entering. What's about this current? We are not sure, so we'll assume that this current is moving away from the node. So assuming this current to be moving away from the node, we'll write, since across this 6K resistor we have a voltage V1 minus ground. So V1 minus ground over 6K is the current flowing. According to Ohm's law, current flowing through a resistor is equal to the voltage drop across it divided by its resistance. Plus, we'll assume current to be rightwards because we are writing equation for node 1 and we have assumed that its voltage is the highest. So V1 minus V2. V1 minus V2 is the voltage drop across this 12K resistor, and according to Ohm's law, dividing it by 12K gives us the current. So this is how we can write equation for node 1. For node 2, the equation is similar. For node 2, now since we are writing equation for node 2, we'll assume its voltage to be the highest. V2 minus V1 over 12K is the current flowing out of this node leftwards what is the current flowing downwards? V2, what's the voltage drop across the 6K resistor? V2 minus 0, the current divided by 6K. V2 minus 0 divided by 6K. According to Ohm's law, the voltage drop across 6K resistor divided by its value. Plus, and we are definite about this current that's leaving. So, writing it 2 milli is equal to 0. Now we have two equations. We can assign them equation numbers V1 and 2. And we see that in these two equations we have two variables, V1 and V2. So we have two linear equations, two variables. We can solve them simultaneously to find out exact values, the numerical values of V1 and V2. There are many ways we can solve these equations. First, we'll have to rearrange both equations. For equation number 1, we have this 12K in denominator and 6K in denominator. This K stands for kilo, milli stands for, M stands for milli. So let's multiply this whole equation 1 by 12K. So 12K times minus 4 milli. What is K multiplied by milli? K is 10 to the 3, milli is 10 to the minus 3. So the answer is a 1. So when K is multiplied with the milli, the answer is a 1. So 12K multiplied by minus 4 milli, 12 fours are 48. The answer is minus 48. This 12K multiplied by this term, 12K over 6K, this is 2 plus 2V1. Multiplying this fraction by 12K gives us V1 minus V2 is equal to 0. So we can write it as 3V1 minus V2 is equal to 48. This is another form of writing equation number 1. Another form of equation number 1. Let's rewrite equation number 2. Now we have 12K in denominator, 6K in denominator. Multiplying the whole equation by 12K will solve the problem. 12K multiplied by this fraction gives V2 minus V1 plus 12K multiplied by this fraction, the answer is 2 times V2 plus 12K multiplied by 2 milli, 12 multiplied by 2 is 24, K multiplied by milli, K multiplied by M is 1 is equal to 0. Right, V2 minus V1 plus 3V2 is equal to minus 24. Now we have equation number 1 and equation number 2, two variables V1 and V2. Solving them, simultaneously solving them will give us V1 and V2. Let's multiply this equation by 3. If we multiply it by 3, this becomes minus 3V1 plus 9 minus 72. Adding 1 into it, 3V1 3V1 minus V2 is 48. This is equation number 1. So adding equation 1 and 2, but before adding them these two equations, we have multiplied equation 2 by 3. So this cancels, this 9 minus 8 V2 is minus 24. So V2 is minus 3. V2 is minus 3 volts, the first voltage. The second voltage V1 can be computed by putting the value of V2 in any of these two equations 1 and 2. Let's put it in 1. 3V1 minus V2 minus into minus 3 is equal to 48. 3V1 plus 3 is equal to 48. V1 is 45 over 3 is 15 volts. So this is all for today's lecture. In the next lecture, we will solve at least one more problem related to nodal analysis, and the student is encouraged to solve more problems from the textbook. Thank you.